Hi everyone, today we'll be looking at transferability of prompt tuning for natural language processing. Prompt tuning is a way in which you can elicit responses from large language models. And prompt tuning basically prepends some soft prompts, and these are virtual tokens which are appended to the input sequences. And instead of training all the parameters of the pre-trained language model, you freeze the parameters of the pre-trained language model and only tune these prompt related parameters. So it can be viewed as an alternative to fine tuning, where you don't have to fine tune so many different parameters, and it becomes increasingly expensive to fine tune the entire language model as the models get bigger and bigger. And it's shown that prompt tuning is promising when you have large language models. But one of the issues with prompt tuning is basically that it takes longer to converge compared to fine tuning. So this paper tries to evaluate if prompt tuning can be made more efficient, and also if prompts can transfer across different tasks, and if prompts can also transfer across different models. And they further go on to study different transferability indicators with a hope to shed light on the important aspects to consider when evaluating transferability. And so they evaluate two different types of transferability of prompts. One is a cross task transfer. So they have a bunch of different tasks like sentiment analysis, natural language inference, ethical judgment, paraphrase identification, question answering, and summarization. And they try some different data sets for each task, and data sets in the same task, for example, like IMDb and SST2. So these would be considered as similar tasks because they both correspond to sentiment analysis. But when you're looking at IMDb and then looking at MNLI, these would be considered as different tasks because one is related to sentiment analysis and the other to natural language inference. So they want to look at cross task transfer, like what kind of tasks are required for prompts to transfer easily. And they evaluate the zero shot transfer performance. So here you have a prompt, say P1, and this prompt is fine tuned for a particular task T1. So usually when you have soft prompts, they need to be trained on a downstream task, and with the same objective as if you were to do fine tuning, which is cross entropy loss. So this prompt is very specific to a particular task T1. And now what we want to do is we want to see if the same prompt P1 can be used for a different task T2. T2 could be similar task to T1, or T2 could be a very different task compared to T1. And we want to see what kind of tasks, through what kind of tasks the prompt is transferable. And then they also look at the transfer with initialization. So what they do here is, let's say you have two different tasks. So typically when you have a prompt, the way you do prompt tuning is you have a particular task T1, you randomly initialize the prompts, and then you basically train it on a particular downstream task and adjust the parameters of the prompt. So at the end of the training, this prompt is fine-tuned on this particular task. So now what they want to do is, let's say we have a different task T2. Instead of randomly initializing the prompts P2, what would happen if we would initialize this prompt for task T2 with P1, right? And then would that affect the convergence? Would that make the performance better? Those are some of the questions which they're trying to look into. And then they look into the cross model transfer. So here what they want to do is they want to look at two different models. Here they use Roberta and T5, the larger versions of them. and they want to see if, let's say you train a prompt P1 on Roberta. Can I reuse this prompt P1 on T5? Right? And so here obviously the embedding dimensions and the semantic space is different for both the models Roberta and T5. So they have a projector which is specifically learning to project a prompt from Roberta's embedding space to T5's embedding space. So that's what they describe here. So they have this source PS. They call PS as the source prompt, right, in the source domain, which is Roberta, and they use a multi-layer perceptron to basically project it onto the target domain, that is T5's target domain, right? And how they train this MLP is by they use two methods. One is distance minimizing. So for a particular prompt PS, right, you already know what the fine-tuned for the same task T, you know what the prompt would be in the target domain. That is for T5 what the prompt would be. So what they try is you have Roberta and you fine tune it on a downstream task and you get a prompt P, right? And then you have T5 and you fine tune it on the same downstream task. Let me call it P1 and you get another prompt. Here they call it PT. Right? So they use this P1 in this MLP to get PS, right? And then they try to make sure that the distance between PS and PT is minimal. So that's the training objective to get the weights and biases of the MLP. And in terms of task tuning, they do something similar where they train this cross-model projector with some task-specific supervision signals. So both these methods where they train the MLP is dependent on a particular task T, right? But they say the projector as such learns to map an embedding or a prompt from the source domain to the target domain, and it is able to generalize well on other tasks as well, and it's not limited to the task which it is trained on, right? And again they evaluate the zero shot transfer performance. And this would be you have a particular prompt P1 which is trained on Roberta. You project it onto say PS and then you use the same prompt PS on T5 and then you see what the performance is. And then the same with initialization. So instead of just using the prompt in a zero shot way, you use PS as a initialization for T5. And then you train and you adapt the PS parameters so that it is more fine-tuned to the downstream task with that particular specific model, which is T5 here, right? So that's what they do. And let's look at some of the results. So here they have the zero shot transfer performance. So the numbers here indicate the zero shot transfer performance divided by the original performance in percentage values. So here you have the source task and then you have a target task and you have the different data sets, and a particular task is color coded. So the ones in blue are sentiment analysis, so on and so forth. So you can see that when you look at the performance, you can see that across similar tasks, which is here, right? All these are sentiment analysis tasks. You see good performance when you actually just borrow the prompt from another data set. But then you see that the performance is not so great when the two tasks are different. Like these are examples of NLI, right? And your source task is IMDb, which is sentiment analysis, and your target task is NLI. So it's the performance is not that great. And a good baseline to compare would be random prompt, where you just initialize a prompt randomly and then you see what the performance is, right? And so in some cases, like for example the movie case here, right? So the source is think this one is interesting. So you train it on the source task is IMDb, but then the target task is movie. And when you evaluate the zero shot transfer performance divided by the original performance, you see it's 101 here, indicating that the zero shot transfer performance is better than the original performance. So you can even sort of get better performance when you reuse prompts from a different data set, right? So we'd call these like similar tasks. So the reuse is definitely good, and sometimes you see that across two different kind of tasks, it's not really that useful to reuse the prompts, right? And the same goes with T5 as well. And another thing which they evaluate is the speed up, right? Which is speed up, they define as the training time of the um, prompt tuning, and you divide it by the training time of the transferability, the transferred prompt tuning, right? And you see that it's usually greater than 1, indicating that it takes much smaller time to actually converge when you use prompts from a related similar task, right? And in some cases, right, here transfer prompt tuning, I think TPT is transferring initialization, right? This is when they transfer the initialization. So sometimes you see that it's even so here the baseline is just prompt tuning, that is, you know, you start from random initialization and then you tune it on a particular downstream task. Whereas TPT is you borrow the initialization from a related task and then you start training on a downstream task. And you see that sometimes it's sort of even better than starting out with random initialization. And also you see like there is a speed up, and this speed up is more pronounced, I believe, in T5, where you can see almost a 50% speed up and better performance compared to if you started off with random initialization, right? And then they go on to look into the transferability indicators. So here what they want to do is, given two prompts, they want to have a metric to compare how similar or how dissimilar they are, right? So they come up with prompt similarity metrics, and they basically look into two different types of similarity metrics. One is the embedding similarity and the other is a model stimulation similarity. So in the embedding similarity, what they do is, let's say you have a prompt PT1 which has L different tokens, virtual tokens, P1 to PL, right? And this is on a task T1. And you have another prompt PT2 on, again, L, that also has L different tokens, and it's on a different task T2. Now the goal is to evaluate the similarity between PT1 and PT2. So what they do is they use a notion of Euclidean distance, right, where they compare the Euclidean distance between PT1 and PT2. So for that you need to get like one vector. What they do is they concatenate the embeddings of each of these. So P1 to PL, they concatenate the embeddings of that, right? And then they generate this P vector, right? So they then measure the Euclidean distance between PT1 and PT2, and they use that as a measure of similarity. And then they also have the C concat, which basically takes the cosine similarity between PT1 and PT2. But with this kind of a concatenation, you may have some dependence on the position of these virtual tokens. So to be invariant to token positions, they basically try to sum up the Euclidean distance and cosine similarity across each pair of tokens between T1 and T2. So that is their average, E average and C average. The other is model stimulation similarity, right? So here what they do is they try to look at the activations of the underlying transformers in the pre-trained large language models to know, like, if two prompts are similar or not. So if their idea here is, if two prompts are similar, then their activations should be similar, right? So how do they come up with a metric? So So this is the output of the feed forward layer, right, in the transformer. Um, so what they do is basically they take this output of the feed forward layer. So this is after the multi-headed attention layer, right? They take this and any element which is greater than 0, they have a 1, and any element which is less than 0, they have a 0. So they just take the output of this and then they get a state vector which has ones and zeros based on the value, whether it's positive or negative, right? And then that's they use this state vector to evaluate if prompts are similar or not. But before that, how are they measuring these activations? So they're feeding the prompt along with the start token, and only this and not the input, right? They're only feeding the prompt with the start token to the large language model. For Roberta, they also have a mask which is appended. For T5, it's just a prompt and the start token. And then they look at the activations. So we saw how the state vector is generated, right? So this essentially has zeros and ones. So now what they do is they concatenate the state vectors across different layers, and they call that as the activation states. So here they say that the higher layers, they are more task specific compared to the lower layers. So they only restrict themselves to the top 3 layers, right? And then they have this similarity metric called activated neurons, right? Similarity metric between two prompts, PT1 and PT2, as this activation states of a particular prompt, the cosine similarity between the activation states of both the prompts. So that is what they call as their similarity, activation similarity, or overlapping rate of activated neurons. You can read this as overlapping rate of activated neurons, and that would be the cosine similarity of the activations of the transformers. And they want to see which of these metrics are able to capture zero shot performance the best, right? And so here is a table indicating it, right? These are the different metrics which we've seen, and then they look at the numbers which are associated with same task and different task, right? And you would assume that same tasks have a higher number associated with them compared to different tasks, and that's what these metrics sort of do across the board, right? The same task will have a higher metric compared to the different task. And then and this is given the language model is the same. So here when you have two different language models, they evaluate the projected prompt and the prompt from another language, from like they evaluate PS, which was a projected prompt from the source language model, and PT, which was a prompt from the target language model, and they assign similarity scores to them. So here they evaluate two data sets, which is laptop and MNLI, and this is for sentiment analysis and NLI. And they look at C average and the overlapping neuron similarity, right? So here you can see that for the NLI, you would assume that the same task, again the same thing, right? The same type task should have a higher metric associated with it compared to a different task. But here you can see that for C average, the same type task is 2.7 as a metric associated with it, whereas a different type task is a value of 4.1. So this is clearly not a very good metric to evaluate some transferability. So they then stick with ON, or the overlapping neuron similarity, right? Where you see that for same type task, you basically have a higher metric associated with it versus different type task. And then what they do is, so you have this similarity metric with which looks at the activations of the feed forward layer in the transformer, and this is across the top 3 layers. And then you also have zero shot performance, right? So with each of these, you generate a rank list of the different tasks, right? And then you compare the correlation between these two ranks, and that's done by the Spearman's rank correlation. And they find that for the ON, or the overlapping neuron similarity, you get the highest correlation between both these lists for both the models, Roberta large and T5. So, so they then say that probably this is very telling that you need to look at the activation of neurons as a way to measure transferability. And yeah, so the main takeaway of this paper is that soft prompts, you can transfer them to similar tasks without any training. And for different tasks, maybe the performance is not as good. And you can, across models, you can basically project prompts from one language model to the embedding space of another and then use it on another language model. And this is a good idea, because as language models get larger and larger, you probably do not want to do the prompt tuning on very big large models, right? So you probably want to do the prompt tuning on a smaller language model and then project it onto a higher dimensional, higher, project it onto a space of the larger language model and then use it, right? So that will save you considerable amount of time in the prompt tuning part. And also these are using prompts across different tasks are also a good starting point if you want to improve the performance of the model on a given task. Also, in terms of transferability indicators, probably you would have to look at the stimulation of the neurons, the neuron activations, to know what kind of tasks a prompt can be used for.